from Princeton. And then he was awarded a Sagan Fellowship at the Institute for Advanced Study. And in 2017, he became an assistant professor at UC Santa Barbara, where he is now. And Tim is an expert in the discovery and characterization of massive planets around nearby stars through direct imaging. And he also does research on stellar evolution, stellar ages, and star clusters. And just in general, Tim is also interested in all kinds of astrophysics and science, and we'll be very happy to talk to anyone about their research. So please do send me an email if you're interested in scheduling a meeting with Tim later this week. And today, Tim is going to tell us about some really interesting research he's recently done on combining multiple planet detection techniques, including imaging, radial velocity, and astrometry to discover and find the masses of planets and brown dwarfs. So for all the people who've called in, please keep yourself muted during the colloquium unless you have questions. And then if you do have questions, feel free to unmute and ask your question during the colloquium if you have one, or you can save it until the end, and then you can raise your hand using the raise hand button. So please take it away, Tim. Thanks.
Thank you. So let's see. This should hopefully work.
It looks good so far. Yes, perfect. That works.
Thank you. So thank you very much for having me. I'm not that far away, and I am desperately looking forward to the time when I can actually come and visit in person. It's been a while since I've actually been to Caltech, but it'll be wonderful. So I want to start by highlighting and thanking my students. So I have my graduate student collaborators there in red. I won't be telling you about everything they're working on, but I would be delighted to tell you about some of their other projects after the fact or one. Mirik and Yi Ting will be the ones who have contributed most to the stuff that I will be showing here. So I'll take this talk as something of a journey, my own journey through the high contrast imaging field, which is a journey of both disappointment and pessimism and optimism. But I think the trend is definitely toward the optimistic end. So hopefully by the end, you'll feel at least somewhat the same way, that it's been challenging, but things are really looking up, and we're going to be in good shape in the next decade or two. We're going to be pretty exciting. So since this is a talk on exoplanets and brown dwarfs, I think it's start from the observation, because this is more observationally driven than I think just about any other area of astrophysics, where we really haven't known what to expect until we started looking. Here I'm showing an animation of the history of planet discoveries, starting with the ones in our own solar system, and later on adding in the first exoplanets. So Uranus down here was discovered in 1781 through just looking in the sky through something that moved. And I think it's a pretty close analogy to where direct imaging has in recent years, where we look at nearby stars and we hope to see something and get lucky. The discovery of Neptune right next to it here is very different, and I think foreshadows what I'll discuss toward the end of the talk, where it was a combination of observations of Uranus and detailed modeling of Uranus's orbit, accounting for Sun and Kepler's laws and accounting for perturbations of the other planets, and things didn't quite match up. But you could make them match up if you hypothesized that there was another ice giant in the outer solar system. And what's more, you could predict its mass, its location. And Neptune was found right about there. So I'll discuss later in the talk how these two planets in our own solar system kind of foreshadow a lot of the things that are going on now. After that, in 1843, it was a pretty lonely time for quite a while, because detecting planets around other stars is really hard. And it's not until around 1990 that it started to become possible. First planets, many of you know, were detected around pulsars using pulsars as ultra-precise clocks. But the first planets around sun-like stars were discovered in the mid-90s, and that won one of the recent Nobel Prizes. So I'll let this movie play one more time, and you'll see a lot of the radial velocity planets fell out in the 90s, work that I know Andrew Howard was in, that his team continues to work And then later on, we'll see transits start to pick up. And then up here in 1995, in just a minute, first definitive brown dwarf was again by Caltech astronomers, Gliese 29b. And we'll also come back to that later in this talk. So a lot of the stuff, this plot, is actually going to come back later in an interesting way. And as the 2000s have rolled on, this has become pretty well filled out. I'll be spending most of my time this talk focused on those triangles, the imaging planets and brown dwarfs. They're to the right in this plot, and they're the top, high masses. I believe the lonely one at low masses is Fomalhaut b, which I'm not sure what your opinions are on that. It's perhaps dubious to call it a planet.
Oh, hi, Tim. I'm sorry to interrupt.
Hey.
This is Tiffany.
Yes.
Your voice is breaking up a little bit. Do you either have a wired connection you could use, or maybe you could turn your video off if the connection is...
I do not have a wired connection. I will turn my video off in the hope that that accomplishes.
Okay, let's give that a shot. Thank you.
I'm going to have to stop my share. I think I'm not a Zoom expert. Halt my video and do that again. Okay. So these different techniques are complementary in many respects. Each one gives you a limited amount of information. The first and maybe the easiest to understand is transits, where it's just a planet passing in front of the star, and what you measure is the size of the planet. So if you have two transiting planets, then you have the relative sizes and the absolute size of them, something like this. That's the exterior information. If you want something more than that, you can turn to radial velocities. Radial velocities give you the mass, but subject to an uncertain inclination. So this might be an example of radial velocity measurement. If you want something better than an m sin I, then maybe find a system with both radial velocities and transits. And this is designed to find a whole lot of these. And then the fact that it transits means it's edge on. And so you know what the inclination is. A face-on orbit will not transit, and you have two masses. But knowing that planets are these massive sizes is as powerful or as thrilling as seeing them. And so direct imaging is special. You get to take a picture of another world, and you get to learn what it's like. If you just had the masses and radii of Venus and Earth, you would think that they're rocky planets with iron cores. But if you have these images, then you can learn an awful lot more. You can learn about the surface and the atmosphere, probe it for signs of life. You can learn about the temperature and the chemistry on Venus's surface, its lack of water. And so that's what we want to do with direct imaging. We want to realize this potential to understand planets. But it's hard. And the basic reason is that planets are faint. If this arbitrary units is a rough spectrum of the sun, then Jupiter today would be way, way, way down there. Separating these two are about 9 orders of magnitude. Roughly, the contrast between an entire floodlit stadium, Dodger Stadium, the Rose Bowl, or what have you, and a single fire eye. And they're right next to each other. So that is well beyond any mission we currently have going. WFIRST, Nancy Grace Roman Space Telescope, might be able to do that with its coronagraphic component. Maybe, we hope. But what people realized about years ago is that it doesn't have to be quite bad. That's what things look like today. But a giant planet formed of some kind of passing cloud of gas and dust. The details of how it forms matter, but roughly speaking, when that cloud of gas and dust coalesces in one way or another, it releases gravitational potential energy. And that means, that means that the young planet will form hot. If we're just looking at this system today, then in the case of our own solar system, it is only doable really because we can block out the sunlight pretty easily. You just wait for nighttime. So in the daytime, you're looking at something like this, but well, wait hours, and it's pretty clear. So this kind of analogous to the coronagraphy that we want to do with other planets and other stars, which is something that Dmitry has done a huge amount of work on over the years and continues to push forward. But for other stars, we don't have a planet that conveniently blocks essentially all of the light. And so we're stuck fighting this huge contrast. It doesn't have to be quite that bad, because what people have realized is that if you have a young planet that is still warm from formation, hasn't had time to radiate all of that energy away, then you're talking maybe 5 orders of magnitude, which is very hard, but now within the range of possibilities enabled by our new generations of instruments. And so direct imaging studies to date have focused on these guys, young, massive planets, basically because the ones we can find with present technology. A cold Jupiter continues to be well beyond our reach, although we're always pushing and hoping that with big telescopes, it won't be beyond our reach 10 years from now. So I'll start out with an older survey for these exoplanets that didn't have as much success as I would have hoped. This was actually part of my thesis as a graduate student, was part of the SEED survey, where we took a rather embarrassingly large amount of telescope time on the Subaru telescope to look for planets around about 500 stars. In order to pull this off in the first place, technology needs to be up to the task. That's something that's happened over the last 20 years or so. 2 pieces of this have been advances in infrared detectors and adaptive optics. And this image, although a bit old, shows you, in a sense, how both of them work together. This is an image off of an infrared detector, mercury cadmium telluride. These things are not CCDs. The band gap in silicon won't allow you to detect an infrared photon. It doesn't have enough energy to kick an electron into the conduction band. So you need something else. In practice, that's meant something harder to fabricate and more temperamental and a lot more expensive. But we've got better at it, partly thanks to the military's interest in such technology. And the other pillar of this is adaptive optics that corrects for the atmosphere in real time. And so you get this image blurred by turbulence in the atmosphere, you undo that blurring, and you get something that looks a lot sharper. If your goal is to detect this faint star next to the bright star, then the fact that you are concentrating this faint star's light in a single point, and the fact that you are removing this bright star's light from that seeing halo, both make a huge difference. You can see that as I flip back and forth. Both of these advances, direct imaging would have been totally impossible. What we actually do when we search for these things is we look for an object next to a bright one. But an image of a star by a telescope, even if you correct for the atmosphere, is going to be some kind of diffraction pattern. It's not going to be a pure point source, because light is a wave. That's not how it works. So this is showing you an actual image taken from the telescope. The color scheme is a little bit garish, and this hole in the middle is from how the detector behaves when it saturates. But you see all these different speckles. These different speckles, some of them are from diffraction, and you might be interested, for example, whether this one, the speckle, whether it is a companion, a star we're orbiting next to this star. What we do is we take a picture of it, and then we reorient the telescope. So you rotate the telescope, that rotates diffraction pattern relative to the sky. Initially, we did this by going into space. You can turn the Hubble Space Telescope around and get any orientation you like. Some years later, someone had the brilliant idea that we happen to be on a rotating planet. And so if you have an altitude as a telescope, then the Earth does this for you as you track the star across the sky. Looks something like that. And so, played as a movie this way, it becomes obvious that this is not part of the diffraction pattern, but is an actual honest-to-goodness companion. It's a star next to this star. You can have some image processing, again, something Dmitry and his group have worked on for years, and you can dig things out a little better below the noise, and you can look for your companions, your planets. So SEEDS used a rather embarrassing amount of telescope time, and well, here are the results. These pretty images of disks, and then if you count carefully, I count 1, 2 things call a planet. And here, depending on how grumpy people are, they might that one or both of these are brown dwarfs. So it was the most encouraging result from this survey. My thesis was supposed to include some planet discoveries, and well, it ended up just being an analysis of the results of this thing, which looks something like the following. We have a few of these exoplanets. By and large, all we can do is say what the faintest thing is that we would have been able to see. We have these detection limits, contrast curves, and that's the extent of it. So my thesis actually ended up being processing and construction contrast curves, and then interpreting what they mean. In order to interpret what they mean in terms of the physical model of star and planet formation, it would be much more convenient to write this as a mass detection limit and detect luminosity changes over time as a mass stays fixed. In order to do that, you need to know the stellar age, so how long the planet has been cooling, and to know how hot it was when it started, how it cooled. So there's a lot that even goes into something like this. The ages are another thing I've worked on a bit over the years. And for the cooler stars like the sun, we can do okay on the ages, even for an individual isolated star. Lynn Hill and Brandt and Eric Mamajek did a lot of the foundational work on this years ago. Basically, the physics is that a star like the sun has an outer convective zone. That convective zone, through physics that I think we really understand, generates magnetic dynamo. That magnetic field couples the star to a wind. So as the wind streams out, the star is locked to its wind by the magnetic field, and like a skater extending their arms, they will lose their momentum to their body as their arms get away. The wind takes away the angular momentum of the star and it's down. So you can use that as sort of clock to date a low mass star or a star like the sun. It doesn't work that way for hot stars. They don't have convective zones near their surface. They don't spin down. And so for hot stars, we need to treat things differently. This is something that my student Mike Lipatoff is working on now. But a few years ago, we did some work to try to understand what age constraint you could get from these rotating stellar models. You do a lot by being to date a collection of stars rather than an individual star. Then you can use the fact that stellar evolution depends really strongly on the star's mass. You get a much better picture. It's still subject to uncertainties. Perhaps so. I realized that stellar evolution still had puzzles when we got into it. Rotation is one of the ones I think still survives as an interesting unsolved problem in stellar evolution. The various codes differ quite considerably on the answer that they get. And so depending on which code and how you analyze it, you can get fairly different answers for what the age is, but still, this is a lot better than an individual star. And so these kinds of things form the bedrock of these direct imaging surveys, the ones where we can date a collection of stars and get reasonable ages to infer masses, planets from luminosities. So that with 2 detections out of all those star planets, if you will, what can we actually say about the planets and brown dwarfs? What I did to try to answer this question was I took these stars and I assembled the best collection of substellar companions that I could from the whole sample. I didn't have the complete final results from everything at the time. And I modeled what we would actually see. And I found that, accounting for all the completeness, all the little details, that a single distribution of companions extending from all the way up on dwarfs to very low mass brown dwarfs here basically explain everything. One way of interpreting this is that if you have a population of higher mass brown dwarfs, things that formed out of a collapsing gas cloud like a star, and lower mass things called planets. Stars on one hand, big planets on the other hand. Then we kind of saw the failed stars. We saw low mass dwarfs, but we know there are lots of planets down here. And it has a whole bunch of them. But, well, we didn't see them. So in that sense, survey is a major disappointment. We found a few things, but this huge collection of planets that we know are hiding somewhere around here, we didn't see them. And so the next challenge is, well, how are we going to do that? How are we going to get these? There are a couple of different answers to this question. And I'll spend the rest of my talk talking about primarily two of them. So extreme adaptive optics are one component. We have an extreme adaptive optics implemented on the Subaru telescope now called SkexAO. GI has an extreme adaptive optics system built into its instrument. Sphere also has one built into its instrument. So these are significantly fancier and better than that adaptive optics system that I showed at the beginning that made that nicer image of the star cluster. Second, something I'll talk about in more detail, is the transition from camera to integral field spectrographs. And I'll talk about an integral spectrograph that I've worked on. The third thing, the 30 thing that we're a part of at UC, Caltech is also part of, hopefully it works out. And then something that certainly JP is a part of is W-First AFTA, which now goes by the Nancy Grace Roman Space Telescope. And that should have a coronagraphic component that'll shine after these companions. And finally, at the end of the talk, I'll discuss astrometry, which I believe is emerging as a saving for this field now and is really going to solve a lot of our problems. So in the next part of the talk, I'll talk about the field spectrograph aspect of this, and that's going to help before I transition to astrometry and how that combined with field spectrographs is going to really start to solve our problems. So there's the acronym. It's an instrument that we built a few years ago for the Subaru telescope. I didn't actually have a hand in building it. I did write the data reduction software, and I have certainly been involved in using it over the last few years. So I don't know how many of you are familiar with an integral field spectrograph, but it works a bit different from a camera. And I think it's really cool. I'm going to spend a couple of minutes going over the basic layout and how it actually works. If you have a camera, you have an imaging system. Then you have some optics, makes an image of the sky, and you put a detector there. For an integral field spectrograph like Keras, you do not put a detector there. You put a lenslet array there. What that does is it takes all the light from this lenslet, puts it into a point. All light from this lens, it puts it into a point. So at the next image plane behind this, you don't have you have an image, you have a bunch of tiny little points. You have an image kind of condensed into this little pinhole grid. You then have a lot of unused space on your detector. You use that unused space to disperse it, spread out each one of those points into a spectrum. So this is an optical setup that gives you a spectrum from each lenslet. Then you have to take this detector image and reconstruct the data cube, the image at all wavelengths. To walk you through what that looks like, this might be an image that you would see if you just had a detector, simple imaging camera. But instead, we put a lenslet array in front of this. And so this image turns into a bunch of bright spots, bright little points. Most of this is empty space, and so most of these detector pixels are currently being wasted. We then use them to spread out the light into all these little tiny spectra. So this is a real image showing all of these microspectra. Here's the spectrum of light that fell on one lenslet. It's not that long. And spectra don't have very good spectral resolution. In fact, the spectral resolution here is about 20. So if you're used to something like high res, 50,000, then you probably wouldn't even call this a spectrum, but we call this a spectrum. These dark spots here and here are from regions in the atmosphere where the light is absorbed. So where it's bright, here you see the shorter wavelengths where the star throws out more photons, and you see these dark bands where the atmosphere absorbs. So there are about 20,000 or so of these little spectra packed on this detector. And then we need to go from those to the image as a function of wavelength. And now you see it. Now you see that I have a diffraction pattern of this star. These points over here, here, the four grids there, and their harmonics are actually little points that we put there on purpose. They're copies of the central star that we've diffracted out to positions by putting a known pattern on our deformable mirror, and then we block out the central star. So these preserve some information about the star so that we can triangulate where it is and know about its brightness. And then you're just seeing the physics of diffraction, where that image expands as a function of wavelength to fill your detector. If you look closely, you might see that there's one point in here that does not seem to expand with the diffraction pattern. So another 5 seconds or so before I put a big circle around it. And that point oops, there it is. So that is actually a brown dwarf. In the early part of this talk, I showed you how we detect these things by waiting for the Earth to turn so that I distinguish a speckle from an actual companion, like a star, planet, brown dwarf. It's a single 20-second exposure. I didn't need to wait for the Earth to rotate. I could use the scaling of light with wavelength to do for me, the scaling of diffraction with wavelength. So that's a powerful tool that these integral field spectrographs open up to us, called spectral differential imaging, to distinguish the chromatic behavior of diffraction and an actual companion on the sky. In the still image, you can tell the difference. This is what Keras actually looks like. It's not that big. In our case, the adaptive optics and all that fancy stuff out in front, and it's less than a meter squared. It has this nice Iron Man red finish on it, on a single piece of aluminum. Inside, if you're into instrumentation, that's what it looked like before we had some additional baffling, some additional black tunnels that would block out scattered light throughout the instrument. And just to show you that this spectral differential imaging does indeed help, this is showing the HR 879 planets, at least 3 out of the 4 of them, the 4th one there, without spectral differential imaging, and then with. And so that spectral differential imaging gets us something like a factor of 2 gain in performance, which is going to be important because it stacks up on top of all the other gains that we get. Minghan Chen is a student of mine. He's working on finalizing the pipeline for this and the post-processing. And I also want to highlight the work of Jason Wang, who has quite a bit with Minghan and built the PyClip package on which this is based. So our work here owes a very significant debt to Jason and his work over the year. Another thing that we want to be able to get here, beyond just contrast gains, is to take advantage of the fact that this is an integral field spectrograph. And if we have spectra, then we have a shot at learning about the physics of these worlds. When I showed a picture toward the beginning of the talk of Earth and Venus, one of the goals here is to actually take spectra of these worlds. This is showing a spectrum taken with the OSIRIS integral field spectrograph, an older one on Keck. And this, depending on your perspective, is either a super Jupiter or a brown dwarf. It's a spectrum. It looks crazy, but in fact, most of these are not noise. If I put a model here with no noise whatsoever, a lot of these wiggles are repeated. Those wiggles are signatures of molecular absorption. I can't possibly do this to the people at Tech who are working on inferring um, the atmospheric species from spectra, but there's an enormous amount you can gain by trying to model this and figuring out how much carbon monoxide, how much water, how much methane is in the atmosphere, and what that means for the chemistry. Even at resolutions that we have with Keras, which are very, very from that resolution with OSIRIS, you can still see many of these features from, in this case, the carbon monoxide bandhead and methane and water. And it's showing as a function of temperature, the relative populations of these different species really change. The chemistry that's thermodynamically favorable changes abruptly or changes quickly with temperature. Different temperatures, clouds and hazes also form. And if cloud or haze forms high up in the atmosphere, then it blocks the light more or less uniformly and makes the spectrum much smoother. So by looking at the shape of this spectrum, you get a handle on all these different things: temperature, chemistry, and clouds. Just to show you what you can do even now with these detections of molecules and how you don't necessarily need to be able to resolve individual lines. This is showing what would happen if you had a concentration of methane like what's in the Earth today if you increased it. So this is a bit higher than the pre-industrial level of methane, but if I crank it up higher, higher, and higher, and higher, then what you find is that you basically lose all of your photons over in this part of the spectrum, but you keep them in this part of the spectrum. So at the shorter wavelengths, you'll be able to see deep into the planet or brown dwarf, and it'll look bright. At these wavelengths, you won't be able to see deeply at all, and it'll look fainter. You're seeing a colder top of the atmosphere. This is something that is borne out by actual detailed models, and it becomes apparent as methane becomes thermodynamically favorable around temperatures below 1,000 Kelvin. This was one of the original ideas, to be able to find exoplanets and brown dwarfs by taking advantage of this. Didn't work out all that well, but still, when you image one, you can find conclusive signs of methane in its atmosphere, where at the shorter wavelengths, you should be able to see deep in and see the hot interior. It shows up. At the longer wavelengths, it's gone. So there's a lot that we can do if we can actually image these things and measure their spectra. There's a whole suite of atmospheric science that is open to us. But this has proven really hard. So all that time on big telescopes, depending on exactly how you're counting, something like 10 or 20 imaged planets. It's been a disappointing yield. I could convert this to dollars in terms of the amount of money spent on instrumentation and telescope. If I did that, then each imaged planet would have cost something like 100 times one of these Kepler satellite planets, because Kepler, while it was expensive, got more than 100 times as many planets as these direct imaging surveys, and they weren't that different in cost. So imaged planets are more valuable in many respects than visiting planets, but they're also a lot more expensive. And we've looked around the nearby young stars. We have an endless set of stars to look at. So what next step? What are we going to do? And that brings me to the last part of my talk, which is on astrometry. I think is going to go a long way toward bailing us out of this conundrum. This is a picture of Gaia satellite, which is currently observing. It was launched in 2014. It is actually already at the nominal mission and into mission. So if all goes well and nothing breaks, Gaia will observe for another 4 or 5 years before it finally runs out of the fuel it needs to maintain its position and orientation very precisely. And so the Gaia data we have today only extends for about 2.5 years, 3 years. That's the data that was released last December. So Gaia is still observing, and the data releases are well behind the actual progress of the mission. So this is something that's going to be evolving rather quickly over the next few years as Gaia continues to take new data, and as that new data plus old data gets released. The team's been wonderful about all of this. It's just that there's a huge amount of data and it's really challenging to understand. If you take a look at the Gaia catalog, though, what it tells you might not seem to be so useful for finding planets around nearby stars. For radial velocity, you look for a planet by measuring the tug along the line of sight, the reflex motion of the star along the line of sight. You can try to play the same game with astrometry, where you're measuring the reflex motion of the planet or of the star not along the line of sight, but across the sky, looking for an acceleration across the sky as the star is tugged by something. But Gaia doesn't have any accelerations yet. And that 2021 has actually been pushed back to 2022. Everything got delayed a few months because of the pandemic. So 1 billion positions and proper motions from Gaia, incredible precision, no accelerations. What we do have, at least for 100,000 stars, are positions and proper motions that another satellite, Hipparcos, measured about 30 years ago. What that gives us is something like the following. If I have these two positions represented by these two stars and these two proper motions, in fact, I can think of this plot having 3 proper motions on it. One from this guy, one from this guy, and then one from the different positions, because I know very precisely how long it was between the Hipparcos and Gaia missions. So I can take these 3 proper motions and look for differences between them. This green one is really important because I get to take the positional errors and divide by the time. Because there's a long time between these 2 missions, the denominator of this gives very small error bars to this green proper motion. And so effectively, I can compare this green long-term proper motion to this Gaia proper motion. Incredibly, if I can also measure radial velocity for a planet or for a star, then astrometry and radial velocity are both measuring acceleration in an inertial reference frame. Once the radial velocity team corrects for the motion of the Earth and places everything in the center of the solar system, that's pretty close to an inertial reference frame. They're measuring accelerations with respect to that. Likewise, for astrometry, you're measuring accelerations with respect to the International Celestial Reference Frame defined by distant and relatively fixed quasars. So those give you the 3 components of the acceleration vector. It's just Newton's second law. If you also measure the projected separation, then if you look here, you have 3 equations and 3 unknowns. Amazingly, the mass of the star doesn't show up here. It doesn't matter. So it doesn't matter whether you can trace out a full Keplerian orbit. In radial velocity, that's very important so that you can use Kepler's third law, t squared is proportional to a cubed. Here, it doesn't matter. As long as you have a radial velocity acceleration, an astrometric acceleration, and a projected duration, you get the mass. And that's not something that's been possible before. In order to do this, though, you need to be able to statistically compare these proper motions. And that turns out to be something you can't just do if you download the catalogs. If I compare these proper motions for a sample of stars that I think are constant proper motion across the sky, and I normalize by the uncertainties appropriately, I don't get the Gaussian that I want. The green distribution there is what I should have if all the errors are correct and all the data are behaving perfectly. And it doesn't look like that. If I look at the Gaia proper motion differences, it looks even worse. The takeaway here is that if you just go and you download the Gaia and Hipparcos catalog and you do these naive differences, error propagation, you are not going to get the right answer. And your errors are probably going to be a lot higher than you're assuming. So That means the next step is to cross-calibrate the two catalogs and put them into the same reference frame, make a new catalog that does work for these purposes. And so that's what I did in 2018, was to cross-calibrate Hipparcos with the second Gaia database, which took place in April of 2018. To show you why this is necessary, I'm taking the difference between two proper motions, the positional difference and between the Gaia proper motion for a whole bunch of stars. And you can see that they all seem to be accelerating up and to the right. This is not physical. It is due to calibration issues in the catalogs. So if you try to fix this with some kind of a global correction, then it looks better, but you still see a little bit of asymmetry in the top right. You can a little bit better where you're trying to be careful about not overfitting and keep things straight spatially, and you get your correction. And now, at least, it seems nothing is accelerating in bulk. I don't seem to have any large-scale systematics on the sky. You also have to worry about your uncertainties. And the uncertainties end up having all kinds of little things, little issues with them. As one fun example, there are several different Hipparcos data reductions. The most recent reduction was done by a single person over 10 years, really a labor of love. And it's this huge black box, but well, everybody uses the results. It turns out that this new reduction, it's better than the old one, but not that much better. And you can do better still by just averaging them together. Kind of amazing, but it's something that we were able to show with 150 sigma significance. So what this gives you are three propositions that you can use for orbit fitting with calibrated uncertainties. You still have to be a little bit careful. I know that several people here are working on this orbit fitting, and so I'll call your attention to just a couple of things, although I'll be delighted to discuss these in gory detail in person or in private. First, Hipparcos does have individual position measurements that go into this, but be very, very careful of them. There are systematics and there are even bugs. And then keep in mind that these proper motions are not instantaneous measurements. These satellites measure positions many, many, many times and fit a line to them. I'll show that in a minute. And finally, the Gaia catalog is given a time of 2016. The Hipparcos catalog is given a time of 1991.25. This is just the time of convenience. It's a little bit artificial. So when you're actually going to apply this for orbit fitting, that's what the catalog is for, but there are some subtleties. With that said, after doing all these calibrations, it looks pretty good. These do look like they follow the green line, which is what you would expect for perfectly behaved residuals, pretty nicely. And likewise for Gaia, unless we're talking about these very bright stars for which there are still systematics in the second Gaia data release. I mentioned a couple of caveats a minute ago, and we are trying hard to make sure that we are also providing the tools to deal with them. So my student Mirek, name but no relation, has a tool now that's submitted to fit for the proper motion across the sky by modeling what Hipparcos or Gaia would have seen. For both Hipparcos and Gaia, we know when and where they were looking, even if we don't have the individual observations for Gaia yet, and even if we're not sure, we can always trust them for Hipparcos. And so this enables you to take a synthetic orbit of the star about the center of mass and to model what one of these astrometry missions would have seen. And you can then go and use that in your orbit fitting. And so that's his piece up here, submitted, should be out. We're trying to coordinate several things, but should be out in a month or two, I think. And the other piece is an orbit fitting code that we have also submitted, for which we intend it to work natively with Hipparcos and Gaia astrometry. And we have prioritized speed over being as pedantic as something like Sarah Blunt's Orbitize or BJ Fulton's Radial. So hopefully this additional orbit code fits in nicely and complements those two for this kind of purpose. Different data sets, but where you really about having it optimized for speed so that it runs a few times faster. I can show you at the end if people are interested what tricks we use to do that. And so with those, we can fit orbits with Gaia today. And I'll spend the last bit of my talk showing you some of those results and some of the promise we have for the future. At the beginning of this talk, I showed the directly imaged planets, and one of them was Gliese 229b, not really a planet, but the first brown dwarf ever to be imaged. A discovery that happened right here at Caltech with Sri and people who were at the time his students and postdocs. Now, this was the prototypical brown dwarf, very cold, and the initial estimates of its mass ranged from something like 20 to 50 Jupiters, depending on what you assume about its age. But actually measuring its mass has been beyond our reach, well beyond our reach for a long time, but no longer. Now we can measure the reflex motion of the star, and we can use that to measure the acceleration across the sky of the star due to the brown dwarf. We have incredibly precise measurements of where the brown dwarf is because we have years of Hubble imaging, and we have radial velocity monitoring thanks to the California Planet Survey and other groups. And so we have everything we need to get a mass of 70 plus or minus 5 Jupiters. And my student Mirik is working on a refinement of this. If you believe it, then the acceleration of the star due to the brown dwarf in the data release is about 100 sigma. And so with that date, we get something like a 1%, maybe 2%, no, it's about 1% measurement of the first brown dwarf ever imaged, which is just astonishing. You can kind of get a sense here of what the orbital period is. It's more than a century, but it doesn't matter. It doesn't matter that I'll never see this thing complete a full orbit. We can still measure its mass to incredible precision. And that lets us go back and finally test these models of brown dwarf formation and evolution and see if they're getting the physics right. The physics here shouldn't be all that complicated in the sense that the interior of this should be convective. And you have an atmosphere and people who have spent a huge amount of time trying to get those atmospheres right. You join them together, you do the best you can, and then you can compare the masses that would give you the observed luminosity at the observed age with the dynamical mass that we go out and measure. For a lot of these systems, we have pretty good agreement with these standard models. For Gliese 229b, the agreement isn't so good. And so some of these brown dwarfs seem to be heavier than we would expect. And I think that's a mystery that is starting to come up now. Why are these things more massive than we would expect? Maybe Gliese 229b is an unresolved binary. That itself would be really cool. And it's something that I hope to be able to investigate maybe with some of the people here. The new constraint on Gliese 229b's mass, which is going to come out hopefully in a few weeks, is going to be something like this, and it's going to be 5 times more precise than what's shown here. So this is something that's progressing very, very fast. Here's an example of what we hope to really do more of, to use this astrometry not just to get masses of things we already know about, but to tell us where to look for more companions. Hipparchus and Gaia look at the whole sky. They're not picky. They don't need to decide which stars to observe in advance like we do for direct imaging or like you do for radial velocity where you assemble your target list. Astrometry looks at everything. And so you get to pick the stars that are accelerating and look at them with your imaging and your radial velocity. Here's an example of a star that we targeted for the reason it was accelerating in Hipparchus and Gaia. So we pointed Subaru at it, and we imaged the brown dwarf. Now, because we have a measurement of the astrometric acceleration, and in this case have a few radial velocity measurements, that was enough to get a dynamical mass, even though these equations that we have extend over just a year or two, over almost a 100-year orbit. Again, it doesn't matter. And that's one of the amazing things about this new approach, where we can combine these different data sets and these different analysis techniques. We can abandon that just getting lucky aspect of direct imaging. We can, in effect, load the dice in our favor. And then once we do pay dirt and we do find something, there's a lot we can say off the bat. Here's an example of a radial velocity detected brown dwarf, where there is a published orbit, but it turns out that that published orbit, the chain wasn't converged. If we throw in the astrometry from Hipparchus and Gaia, then even though it hasn't been imaged, we have a mass and we have a location. This is reminiscent of the case with Neptune, where in the case of Neptune, by analyzing Uranus, we knew where to look and we knew exactly what to look for. Again, here, we know exactly where to look relative to the star, and we know exactly what we're looking for. In this particular case, it's going to be really challenging. This isn't very far from the star, and the star is fairly old. So this is going to be a really difficult measurement, but we're going to try on the VLT. We think we have a shot at it. And we're not doing a blind search at all. This is, again, part of a new paradigm, if you will, of a targeted search where we know what we're going to find and where. And it's only possible because of the astrometric surveys and because of the many years of radial velocity monitoring. One more example from work by my student, Mirek. This is an analysis of the planets around Beta Pic B and C, where we combine the astrometry from Hipparchus and Gaia with ultra-precise relative astrometry from gravity. Jason Wong has had a huge part in this, and radial velocity from the European group. And what he's done here is he's derived masses for the planets Beta Pic B and C. So here we have, honest to goodness, dynamical masses of directly imaged planets. This plot here is showing that in these planets, the fact that there's more than one of them perturbs what you would expect to see from the orbit. So we had to worry about that using Orvara, and you would have to worry about it in another code. I know Sarah Blunt and Jason Wong's Orbitize also does this. We found that we were able to do things satisfactorily and get, honest to goodness, dynamical masses that are reasonably consistent with our expectations from theory. So this is in press now. Gaia released another data set recently. So everything I've shown you so far is from Gaia DR2, which is already, hard to believe this, already almost 2 years old. Gaia early DR3 came out last December. It's based on more data from Gaia DR2, but not that much more. 33 months instead of 22. But they also significantly improved their processing, and because they have a longer baseline, it helps more than you might think for proper motion. If you're just measuring position, it scales with the square root of the number of measurements you have. But if you're measuring a motion across the sky, there's also an extra factor of observing time that you get. So you gain a huge amount by observing for longer. And that's one of the reasons why Gaia is going to have an extended mission and why I'm so excited about it. Between the existing Gaia DR2 and DR3, we gain in precision by something like a factor of 3. So today, thanks to the new Gaia data release, we can do 3 times better than the kinds of things that I've been showing you so far around stars in this magnitude. In order to do this, we have to redo all of the cross-calibration that I did for Gaia DR2. That paper is submitted, and with a favorable referee report, should be out within weeks. I do want to continue my special shout out to the radial velocity teams. In order to do this cross-calibration, we needed a sample of stars that were not accelerating. And it would be circular to try to get that from Hipparchus and Gaia themselves. And so to get that sample of stars, my astrometric standards, I turn to the radial velocity teams. They have been monitoring these stars for decades. And so I can then point to a collection of hundreds of stars that are not accelerating along the line of sight. I can convert that precision to across the line of sight, and there's always a chance that an orbit is oriented just so that it would trick me. But the purity here should be very, very good. And indeed, it works. So if I take the formal Gaia uncertainties, then these distributions are broader than the black one, which represents perfect errors. But a modest error inflation brings them into statistical agreement. And so with that, I can cross-calibrate Gaia EDR3 to Hipparchus. And then we can go and we can, as a first step, rederive all these masses with this free precision. And we can also go and fit orbits to long period RV planets and get the inclinations, get masses and not M sin I's. I know this is something Jerry Zhuan has worked on. I think he's hoping to work on something else, but I'm still hoping that he spends some time on this because it's been a pleasure talking to him about it. But look for my student Yiting Li in the next few weeks. We'll have a proof of concept and some masses and inclinations, honest to goodness, of some of these classic radial velocity planets combined with up to 1% mass measurements for brown dwarfs, even if their orbital periods are longer than a human lifetime. So that's all coming out very soon. So I want to leave it there, that there is an awful lot to do, and astrometry is really starting to bail us out. It's time to think about how we can target stars for these direct imaging surveys where we can be fairly confident that we'll see something. And then once we do, we'll be able to get a mass and an orbit right away. We'll be able to do things that we've never been able to do before. And I think it's going to involve a lot of work at the intersection of astrometry, direct imaging, and radial velocity. They all bring a unique constraint to this problem, and the three of them together just nail it down. So with that, I will wrap up, and I would be delighted to take any questions.
Hey, thank you so much, Tim, for a really excellent talk. And those are really exciting results. I look forward to seeing some of those papers coming out soon. It's nice to hear about our field moving beyond blind searches.
Yes.
So yeah,
I've had enough of those.
Yes, I appreciate the positive ending of our field. This is good. So if you have a question from the audience, please raise your hand. I see Lynn has a question. Go ahead.
Hi, Tim. Thanks for the talk. I was wondering with the models and the 229 mass measurement and the comparison to predictions from theoretical models. So your overestimate, your claim of the mass trend seems to be consistent with that for young pre-main sequence stars, which are also fully convective. And so I'm wondering if you have any thoughts on exactly where the problems might be, or if you've gone down that path, or this is just the beginning of this exercise.
So as I understand it, if you have a convective interior, then how big it is and how the light gets out depends on the atmosphere, the blanket you put on top. And that if you increase the opacity, the thing actually ends up being a little bit bigger, and at a fixed age, you would infer a slightly lower mass. And so if you go here,
Tim, would you like to put your video back on, by the way?
Sure.
Thanks.
Let me see. Here. So these Burroughs models had very low opacities, or lower opacity than we currently understand, because it seems like as we've improved the fidelity of the physics, you find new sources of opacity, and those have pushed the inferred masses lower at fixed luminosity, at least at these. So I'm not sure how to make that problem go away. It's kind of perplexing to me because it's a lot easier to imagine that someone forgot a source of opacity or didn't model it properly than that they have really overestimated the opacity. There are people in the field who are very good and who I respect very much, and I don't have a really good answer either. Also, as you get to these high masses, I'm struggling to remember exactly what it is, but I think you get a little bit of an additional energy source in the core from crystallization. And any additional energy source that you get is going to make this problem worse because you're going to need less mass to achieve this luminosity. So I'm not sure how you solve it. It is a binary, that's cool, and that's something that I'm hopeful we can check by doing direct velocity measurement. The astrometry is already really precise. With milliarc second photometry over several epochs from and we have a few more epochs from Keck with comparable precision and not quite as good, but still very high. Hope that we can rule out decent parameter space for a binary companion. But the answer.
Oh, I think you missed the last sentence that you said. Can you say that one more time?
Oh, I'm perplexed. I don't know what the answer is.
Okay.
And I'll just comment, there was a talk at the Cool Stars conference this morning about the next generation of these models beyond Cond and the improvements that they've made, which seem to improve the photometric comparisons. So hopefully the masses will be improved as well.
I hope so, because for a lot of these guys are at decently high masses and ages and seem just fine. For 229, the agreement isn't great. The age that you would infer to get agreement at all is very, very old. And I know Rebecca Oppenheimer too happy about the prospect of the age being old and the mass being high. We've had a little bit of a back and forth over that. But I guess I can't argue with 100 sigma from the absolute astrometry.
Okay. Do we have, did you have a follow-up question, Lynn, or was that good? Okay. Any additional questions? I have one if there's time. So perhaps I will ask it. Well, I'm curious because you said that if people are interested in the orbit fitting software, can you tell us more about how did you make it faster?
Sure. So the answer is a combination of low-level memory management. So it's in Python, but all of the hard work is in Python. So it avoids the overheads of allocating memory and allocating Python arrays. The eccentric anomaly solver turns out to be the rate limiting step. And I was able to make an implementation of an eccentric anomaly solver that's something like 5 times faster than any other one that I tested. It uses a few different tricks, including judicious series expansions of sine and cosine, where you can be sure that you're within the right range, a very good initial guess, and then you can guarantee convergence to machine precision in a single step. And then it also gives the sine and cosine of the eccentric anomaly to you, rather than calculating them again after the fact. So you basically get the eccentric anomaly, its sine and its cosine, for the equivalent of something like 2 trig calls. Then we also analytically marginalize out the 0 points of every radial velocity instrument, the parallax, and the barycenter proper motion, so that you have several fewer parameters that you have to optimize over in your MCMC.
That's really interesting. So this is something that is not published yet, I think you said.
It's not published. It's open source, but I think you would be well served by waiting a few weeks for us to tidy things up and improve documentation, get the paper out. But
Sounds
yes, if you are interested, and especially
Yeah.
if you want to be a beta tester over the next few weeks, please send me an email.
Absolutely, that's super cool. And Dimitri, you have a question, go ahead.
Hi, Tim. So what are your plans for DR4? And do you think the catalog, the exoplanet catalog, is going to be trustworthy from DR4, given all the inconsistencies you found in the earlier releases?
The Gaia data team, Deepak, is very good. I have been talking to, I've been talking a little bit with Leonard Lindegren, Klaus Fabricius, working with a postdoc in Spain on aspects of the frame rotation. So I'm not plugged into them, but I'm kind of adjacent to them. I have a huge amount of respect for them, and I'm reasonably confident that they'll do a good job. I think that we'll also be able to do checks with DR3. Full DR3 is going to include the first non-single star system fits. I'm not sure exactly what that means, but I think they start to include Keplerian orbital fits. Something that should come out about a year from now, and it's something that we'll be able to check with the radial velocity monitoring and with some of these long-term measurements, something like LISA 229. So there will be several independent checks for a bunch of systems on these planets. But as far as my own catalog, after full DR3 and beyond, it's going to not have any usefulness. I don't know whether that end of its useful life will come with DR3 or DR4, but I don't think it's that far away. And that's not a negative statement about the catalog. It's a positive statement that Gaia is just going to be so good that they're going to do a better job than I can. Hipparcos is going to literally supersede it. Hipparcos is not yet superseded, but a couple of years from now it will be.
Okay, do we have any final questions? If not,